We've already looked quite extensively at one model system called the particle in a box, which is a model for a particle which is confined to some spatial region. So let's now look at another model system which we're going to examine with both classical mechanics and quantum mechanics, and this is called the harmonic oscillator. And we're going to use this for the situation I have shown below for looking at the vibration of atoms inside of molecules. So inside this hypothetical diatomic molecule here, I have atom 1 at some point in space and atom 2 at a different point in space, and they are linked by some chemical bond, which is the distance r apart from each other. So in quantum mechanics, to study a system, what we need to do is define the potential energy of that system as a function of whatever position coordinates we have. And our position coordinate we have is this distance r. So if I was to make a graph here of this function v of r and plot that versus the various distances of r, what would this look like? Well, let's use some intuition to think about it. Well, if we have two atoms in a bond which is very, very short, there's going to be some force which pushes them apart. So at short range it has to have very high potential energy, and that decreases as the molecules go apart. So there's going to be some decreasing in energy here. And there's going to be some part where the distance is an ideal length, where there's no force acting on the atoms, pushing them in either direction, where it's just a minimum in the potential energy, what we might call the average or minimum bond length, or minimum energy bond length. Then there's going to be some distance where the bond length is getting quite long, and there is some force which pushes the atoms back together and tries to hold that bond together. So there's going to be some region here where we have a low potential energy, and it's going to be increasing as we pull the atoms apart. And then finally, at very long range, these two atoms will dissociate, their chemical bond will no longer be there, and they will be non-interacting. There will be no forces between them. And so the potential is again going to be flat with respect to increasing r. So we can define any position on this curve arbitrarily to be the zero of energy, but let's just go ahead and pick that r equals infinity is r is zero of potential energy, because then our reference state is the two non-interacting particles. Okay, so we got that there. Then we said as we bring it in, it interacts stronger and stronger, reaches some minimum, and then very quickly, let me do better than that, reaches some minimum and then very quickly hits some potential energy wall, which goes up like that. Okay, so this is just a crude model based on intuition. There are some better models for what this functional form might look like, one of which is called the Morse potential, which we're going to look at in more detail later. But using more analytic types of forms for this potential energy function is going to be complicated. And we know that the Schrödinger equation is a second order partial differential equation. It's an ordinary differential equation if we're just considering the spatial part. So we want to make a potential energy function which is as simple as possible. So what we're going to do is take a Taylor series around this type of function, which we know it has to be. So the first term is basically just, and we're also going to expand this around this lowest energy point here. So this minimum energy that we're talking about, we're going to call this as R naught, or the minimum energy bond distance. You might call it the bond length. And so expanding around this point, we can call anything we want to arbitrarily be zero. So the zero order term in the Taylor series we're just going to call zero, so we don't have to carry around any extra constants. Then the first order term is a linear term, and that's some constant times r minus r naught, which is that constant is the first derivative evaluated at this point. And the first derivative at this point is zero because it's a minimum energy function. So the first order term is also going to be zero. Then the second order term is a quadratic term. It looks like 1/2 times some constant times r minus r naught squared. And for the second order term, that constant that I mentioned is the second derivative evaluated at the minimum in this energy here. So this quadratic function is going to be a parabola. So if I draw a parabola here, which kind of closely models the system around the minimum, and I'm also going to define this coordinate x, which is equal to r minus r naught squared, then the potential energy I have, if I'm defining it with respect to x, is going to be v of x, which is going to be 1/2 some constant k x squared. And this constant k, like I mentioned, is just going to be the second derivative of this more complicated potential energy function evaluated at x equals 0 or evaluated at r equals r naught. So this is the potential energy function that we're going to throw into the Schrodinger equation later, and we're also going to solve Newton's equations for the same potential energy function. And we're going to see where this leads us in terms of what the allowed energies are of a vibrating molecule, of some vibrating mode inside of a molecule, and also what the wave functions will look like for this, what the classical trajectories would look like, and then how good that ends up being for predicting things like vibrational frequencies in experiment. So that's where we're headed over the next couple of models, looking at solving the Schrodinger equation for this type of potential energy function and looking at modeling vibrations inside of molecules.